use the integration that gets to 0. So these two components, they cancel out, and what you would survive with only this term. All right? So the final force, what we find is F equals to from 0 to pi over 2, from 0 to 2 pi epsilon naught of E z squared minus half of E squared r squared sine of theta cosine of theta d theta d phi along the z direction. All right. So I'll just give you the result what you'd find for this part. So that's for the plane part, and for the so this is what you find after you carry out the integration using those components for the electric field. You ended up with F1 equals to 1 over 4 pi epsilon naught q squared over 8 r squared along the z direction. Okay. So that's not the whole force. So this is what we found by considering the spherical surface. But we have to consider also the plane surface. So what should be the area vector for the plane surface? Huh?
R cubed, or r squared z hat.
Z hat, yes. So, so this is the surface that we are considering. We already done for this one. So if this is the z-axis, and this is the x, and this is the y, so dA I can write it as it doesn't have x component, it doesn't have y component, so 0, 0. And how can I express the A in polar coordinates for the plane surface? This surface. Yeah, in polar coordinates. Yes, so we can write that R, dr, and dV. And how can we express the electric field on this plane? So the electric field, just if I express it, so this is going to be Q over 4 pi epsilon naught, and here I should have R over R cubed along the radial direction. You agree? Do you know how we get that? Okay, so then based on that, and if I express the unit vector in terms of the theta and phi, this is going to be Q over 4 pi epsilon naught, 1 over R cubed into R vector, R times the unit vector R gives you the vector R. So that would be E is going to be Q over 4 pi epsilon naught 1 over R cubed, and the components are sine of theta, cosine of phi, x hat, plus sine of theta, sine phi, y hat, plus cosine of theta, d hat. But what do we know about theta? Yes, since we are evaluating on this surface, eventually theta is equals to pi over 2, and that would give you components for the electric field that is along x and y only. So that would tell you Q over 4 pi epsilon naught 1 over r cubed of sine of theta is sine of pi over 2, which is 1. So you have cosine of phi x hat plus sine of phi y hat. Oh, this is on the plane surface. So what does that tell you? That tell you X is Q over 4 pi epsilon naught. Q over 4 pi epsilon naught. 1 over well, should be R. There should be R here. There should be R here. So R over R cubed cosine of phi, and EY is going to be Q over 4 pi epsilon naught R over R sine of phi, and EZ is 0.
What happened to the RQ?
Huh? Yeah, I'm trying to rush it. I want to finish this chapter. Yeah, this is a very lengthy example. So, but you know, we have to do it. Tensor, the Maxwell stress tensor is very important when we talk about relativistic electrodynamics. So, all right. So these are the components. Then after this, you can easily find the elements of the matrix for the Maxwell stress tensor. So just if I try to get help from here. Okay, first, based on what we have, just only for the information for the area vector, this is, well, dA is, I should have put a minus sign, y, because the normal always is pointing outward and it's pointing in the negative z direction, so I should put a minus sign. So based on this information, what survives when you take the product of these two metrics is going to be Txz with that, and Tyz with that, and Tzz with that. All right. So there has to be a minus sign for both. All right. Now, let's look at just the. So this gives you the x component of the force, the y component of the force, and the z component of the force. So what would you expect for the x and the y component? So it should be 0, right? So Txz, this is what you get for the Txz component, Tyz component, and Tzz component, all right? So this is after you evaluated the matrix. Now just look at the results for the force for the x component, which is given by that, right? So Fx is going to be the integral of T dotted dA x component over the plane, over the circular plane, and that is going to be the integral. So it's going to be a double integral of, with the minus sign, Txz r dr d phi, right? So where r should vary from what to what? We are covering the entire plane, so r should vary from 0 to capital R.